recording because I forget to turn on the recording from the beginning with the other section. Okay, now what are we doing here? We stopped with helical gears, and well, if you recall, we talked about the basics. I wanna emphasize on one thing, ya shabab. Again, for those who may forgot, until now we are studying kind of how these gears are, you know, physically or mechanically designed. Like, for example, when we talk about the axial pitch, or when we which is, sorry, this is the transverse pitch, this is the axial pitch, and then we have a normal pitch, and then we have a transferred pressure angle, and we have a normal pressure angle, and we have a helix angle. All of these may seem, and I said this before, I'm just trying to repeat it again for you to understand me here. They may seem to be, why? What the hell? I mean, why are we doing this? And okay, we know that this is BT over tan psi. So what? What does it mean? What's next? So this next is always gonna come, unfortunately. But I promise you, within the next period, okay, these things will come again, and they will become like, more or less, you know, to be optimistic, second to nature. Oh, I know this. That's it. For now, since we did not, I mean, toward the end of the chapter, we will study the forces. You will see each tooth on the spur gear, or a tooth in a helical gear, or a tooth in a worm gear. And you will see all the forces coming in 3 dimension. And all of a sudden, the meaning of the helix angle and start to become better and way more meaningful and impactful in your understanding. For now, just bear with me. It's a little bit boring. However, we're gonna get over this, and then things will get exciting later. Now, if you look at a helical gear, and knowing that this is the helix angle where the tooth or teeth were cut, and if you cut along this line, okay, the teeth and the whole gear, okay, we're looking here from the top view, and then you cut it with that inclination, you will end up with a circle, because the gear is like this, and now it's like you are cutting it down. So that circle that you will end up cutting will definitely have a diameter. And that diameter, okay, if you assume it to be like the radius, or, you know, a diameter of a gear, okay, which is virtual, by the way, you cut it, it's helical gear, but you cut it with an angle psi on the vertical plane. That circle is like a virtual gear. And if you were to imagine that this virtual gear has number of teeth, then the number of teeth on that virtual gear is n prime, which is equal to n divided by cosine cube psi. Now, I know you may not fully appreciate why is this, but if I would guess, I tried also to find a reasoning why these there. There is a lot about gearing, but in my understanding is that this kind of analogy, this kind of virtual teeth, virtual gearing, I think it is more or less an approximation. If you are in a design condition and you say, you know what, I don't have a problem with the thrust, I don't have a problem with noise, I just want, my client said, I have the choice. Should I go with a spur gear or should I go with helical gear? I believe that to some extent, this virtual thing is like a bridge between how can you transform from a helical gear into an equivalent kind of spur gear. I think this is just a little approximation to start with something and then build on it. Do you understand? Better than just starting from scratch. So the rest is very simple. I'm not going to go over this example. I am putting them here just to complement the slides. And if you are the kind of person who would love to, you know, exercise and, you know, study from the slides, you will have examples. Otherwise, these are very simple. I mean, you've been given the number of teeth and BT, and then you find D. I mean, you just apply the equation, you plug and calculate. So what we want to talk about next is the concept of the interference, if you remember it. And when we talked about the interference, we said that if we have a tooth like this, okay, then part, I mean, I'm drawing here for simplicity a spur gear, a tooth and a spur gear. Then what do we have? We said that, for example, we can think of the black portion of the tooth to be involute, and we said that this part, which is now I'm marking with the blue, or if you want, I can mark it with yellow. This is a non-involute, which will end up causing you a non-conjugate action, which we don't want. So we said that avoiding this interference can be made in a simple way, simple state way, by counting the number of teeth. So there is like a minimum number of teeth. If you achieve it, you will be away from this interference. As simple as that. And just for the sake of it, I want you to understand one thing, is that the pressure angle here for along the tangential, or sometimes if we call it the transverse direction, is given to you by this from the previous equations, and we will use this angle inside these equations that will tell us what are the minimum number of teeth for the pinion, for the gear, in order to avoid interference. Okay, now just for the sake of analogy, if you were to make a table and put the first column for spur gear and put the second column for the helical gear, you will see that with respect to interference, we have exactly the same kind of steps. First, we look into the pinion of a helical gear with the same number of teeth. That's what we said before with the spur gear. We said with 1-to-1 gear ratio. So here, the same number of teeth, then the equation, and even the equation is more or less very similar. I think the only difference here is you will see the pressure angle. It's phi t, which is defined as this. If you recall, we had the parameter k, and we said that k is equal to 1 for a full tooth. And then if we have a stub tooth, I mean, the stub tooth is the tooth which is being cut a little bit. Okay, we don't have the entire height of the tooth. This is k equals to 0.8, if you recall. Now, for a conventional standard application, we assume that most of the time probably k is going to be 1. This is now psi, cosine psi, which is the helix angle, and this one is the pressure angle, which is defined over there. All right, if you recall, first we did it for 1-to-1, then we said, oh, what happens if we have gear ratio, when the number of teeth on the gear are different than the number of teeth on the pinion. Okay, and when we said that, we defined m as the gear ratio, and then we had this equation which will give us the minimum or the smallest pinion tooth count, the minimum number of teeth, okay, including M, the gear ratio, including the pressure angle and including the helix angle. Okay, are we good? If you recall, with the spur gear, the next step was to find the largest gear for a specific pinion. Largest gear for a specific pinion. Knowing the number of teeth on a pinion, knowing K, knowing the helix angle and the pressure angle, this equation is also not very different from the spur gear equation. And finally, the rack equation for a rack. We did this. I am pretty sure if you have a good memory, you remember all of this. So it's just the same story. Okay, you can, as I said, you can put them in a table and you will see how they are compared to each other. All right. Now, the next part that we would like to talk about is the worm gear. Now, worm gear, if you recall, we have this is called worm, and the other one, which is the gear, so the worm is like the smaller one, and then the bigger one is called the worm gear. Now, the worm and the worm gear, like they come and get engaged, okay, in this fashion. This is the worm, and this is the worm gear. Do you recall that, ya shabab? So in the side, they are like this. This is the gear, and this is the worm. All right. Now, here, we have this sense of helix angle. You see that? The teeth are cut with an inclined angle. But as mentioned here in the book and in the slide, usually the helix angle on the worm is quite large, and it is small, very small on the gear. And because of this, we are going to specify a lead angle, lambda, for the worm, and we are going to specify a helix angle, which is psi g for the gear. Okay, so in another word, the lead angle is just like the helix angle, but just to distinguish them, lambda is for the worm, psi g is for the gear. Okay, now what else? These two angles are complementary. They complement each other, which means they add up to 90 degrees. Okay, and similar to other gearing system, the pitch diameter for the gear is equal to the number of teeth for the gear multiplied by the, what ya shabab, do you remember what is PT? Anybody? This is the transfer circular pitch, we call it. And if you forgot that, that's fine. Hopefully later when we start dealing with it. Now we are just touching on these gearing system. And of course we have pi as a constant. If we want to know the pitch diameter for the worm, okay, then it is usually selected to fall in the range. So this is the diameter dW. The other equation was for dg, the gear. This one is for the worm. So dW is the pitch diameter for the worm, which is equal to this relation in between c to the power 0.875 divided by 3 and c to the power 0.875 divided by 1.7, where c is the center distance. Okay, now we have also, ya shabab, to define a lead. Look at the lead. It's like the distance here, just like if you recall with bolts, ya shabab, and screws in 307, we told you that if we rotate a screw one single rotation, then it will advance a distance, which we call it the lead. We even give it a symbol, small l, italic L. Here, the lead, capital L, is the same, but for a worm. So if you think that there is a point on the worm over there, then if you rotate the worm one rotation, that distance is called how long that point will travel in an axial direction is called the lead. The lead is px multiplied by nw, and then if we know the lead over here, we can use it to define the lead angle tan lambda, which is equals to L divided by dw. Okay. Now, with respect, ya shabab, to the systems, now we are going to pick specific designs for the gears that suited for certain application. And what we have here is like a standard dimensions and specifications for gearing. So if you look here, we have standard and commonly used tooth systems for a spur gear. It's famous spur gear. So for full depth, we have all of these. You see the pressure angles? 20, 22.5, and 25. I told you once, that says in the book, that once upon a time 14.5 was a common angle, but now it is 20, 22.5, and 25. We have for a stub teeth, which is the tooth which being cut by a little bit, there the dimension, one time we told you for a pressure angle pressure angle 20, we told you that the addendum is equals to 1 over P, and the dedundum is equals to 1.25 divided by P. All right. So these are the equation for each pressure angle. We have here the sizes for the diametral pitch. I'm going to talk about diametral pitch in a minute. So the diametral pitch is kind of the measure for this is more or less like the threading system in bolt. And here we have the manual. Okay, all of this is for spur gear. Then we have for bevel gear system. So for bevel gear, we have, these are the working depth, clearance, addendum and dedundum. We have the gear ratio, face widths, and so on. We also have for helical gears, we have the addendum, dedundum, the pinion, the diameter of the pitch, the gear, pitch diameter, and so on. All of the equation being tabulated nicely in one table. This is very useful. These are the recommended pressure angles and tooth depth for worm gearing. You see, this is the lead angle. This is the pressure angle, phi n. This is the addendum and the dedundum. All right. Now, what I want to show you here is that this is, ya shabab, one of the interesting tools. If you've been in the machine shop, ya shabab, and you probably might have asked for knowing I have this bolt and I have this nut, and I want they don't fit into they don't fit together. And you will ask the question, if you look at the thread, they look the same. So one way to tell what is the mystery over here is to take a dial. They call it a gauge, just similar to this. The gauge has many strips. Okay, each strip is signed with a number, and each strip has different profile. Of course, this is very fine if you look at it. This is very fine teething. This one is very coarse. You see the 1, 2, and so on. So what happens over here is that if you take this gauge and then you try to match it with the thread that you have, if it match, you can go and read and say, oh, this is M4, a metric M4 threading system. It's a fine or coarse. That's what they tell you. You got that. So same goes with the gearing. You can't just guess it. I mean, look, ya shabab, this is a diametral pitch of 4. And look, from this distance to this distance, you have 1, 2, and a little half and a half teeth. But if you look at a diametral pitch of 10, you will see that you have a little half here, then 1, 2, 3, and then half. If you look at this is 26. This is 80. And I think you got what I'm talking about. So this gauge is very interesting. It will just put it, match what is the teeth system that you have, the number. Okay, how much is it? So the next part, which we are going to talk about today, is the gear terrain. Of course, gear terrain is, you know, a term which indicates that there are at least one pairs of gears working together, or even more. Okay, like 3, 4, and so on. Now, what I want to point to, ya shabab, here is that you are definitely familiar with this. I mean, this is not the first time you see it. We talked about gears engaging together, and just for the sake of reminding you, we here have 2 gears. Okay, the first one, let me pick maybe green. So the first one is A, which I gave it a diameter D2. The second one is B, which I gave it diameter 3. And if you see the diameter here is indicated, forget just for now, this is the number of teeth. This is N2, which is 20. This is N3, which is 40. Good. Now, in order to give you a sense of direction, we gave the omega 2, which is the angular velocity, a positive sign following a right-handed coordinate system, which says that omega 2, as it rotates, the thumb is pointing outward, okay, which means that this is positive, toward the positive z direction. The other one, omega 3, is pointing inward, and that's why it is negative. Okay, now that sense of direction, if you want to put it in the equation, then if you recall that what you is the driver and this is the driven, then N3, you want to know what happens to the driven. N3, which is the driven here, is equal to the number of teeth for the driver, which is 2, the number of teeth divided by the number of teeth of the driven, multiplied by N, which is the RPM. And there is a negative sign just to tell you that the direction, the sense of rotation is opposite. So this guy will rotate in the opposite direction of the other one. That's the meaning of the sign. Okay? Of course, you know the origin of this relation. The origin of this relation starts right there at this point when the 2 teeth come together in contact at one point, and we end up saying that V1 or V2 equals to omega 2 R2, and then V3 equals to omega 3 R3. And by knowing logically that these 2 velocities coming from the same point moving in space, then they are supposed to be the same. And that's how we arrive to the relation omega-2 R2 equals to omega-3 R3. Now, omega is related to N because omega is radian per second, while N is revolution per minute. You can switch them off. The radius can be related to the diameter by multiplying by 2, and then the diameter is related to the number of teeth. So that's how we got this relation. So here, as an absolute value, without regard to the sense of rotation, we have N3 equals to N2 divided by N3 as the number of teeth, multiplied by N2, which is the same as the diameter D2 divided by diameter D3 multiplied by N2. N, as I said, is the RPM, revolution per minute. Capital N is the number of teeth, and D is the pitch diameter. If we focus on the gear ratio, mg, it is N3 over N2, okay, which is omega-3 over omega-2, which is, if you give omega and the RPM a sense of K, direction, whether this is positive or negative, then just putting the sign will make sure that you will have this distinction between what is going to rotate in a clockwise, what's going to rotate in a counterclockwise. All right. So it is N2 over N3 or D2 over D3. Now, of course, for a simple gear, all right, for a simple gear system, this is what we discussed just a minute ago. We can also have an internal gearing. I think I need to fix this. If I am not, I think I mixed them up, so don't worry about it. Then here, in this example, we have an external gear, and inside there is an internal. So these two gears, okay, will rotate always in the same sense. So this is different than one gear beside each other. They always have an opposite rotation. So these guys, when this rotate in this direction, like a clockwise, a counterclockwise fashion, this one will also rotate in a counterclockwise fashion and vice versa. So there is no need for a sign. These are positive, but the ratio stands the same. It's just the same. N3 equals to N2 divided by N3 multiplied by N2. Okay. Now, what is important for us is definitely not two gears most of the time. Most of the time, it's very important, but as mechanical engineers, I mean, we mostly make benefit out of this gear terrains when we have multiple gears, multiple shafts connected to each other, okay? So in this example, if you look, we have stages. The first stage, if we look in the top, this is the shaft, and then we have gear number 2. So this is gear number 2. And then we have another stage where we have another shaft over here. Then we have gear number 3. Good. Now, gear number 4 is actually not one single gear. There are actually 2. So gear number 4 is engaged with here. That's number 4. But behind it, there is another gear, which is a little bit bigger. And this gear is number 5. Now, be careful. When gear number 5 and 4 rotate, they have the same RPM, but they have different radii. Okay? And finally, we have gear number 6 over there. So gear number 6 is finally engaged with 5. Do you see this? That's how the stepping is happening. Now, of course, we have in this problem, assuming that N2 is the driver and N6 is the driven. Apparently, you want to know when you drive number 2, what happens to the driven one? There, in the end, number 6. So the number of revolution for 6 is going to be equal to putting the minus sign to check, you know, if this is gonna go in the same direction or not. We have N2 divided by N3 multiplied by N3 divided by N4 multiplied by N5 divided by N6, and then we multiply it by the RPM for 2. So this is the input RPM. And then you have the other gears being driven by 2, okay? And when whatever happens is related to these ratio as they multiply or divide. So we are going to introduce train value E. What is the train value E? It is the product of the driving tooth numbers and then divided by the product of the driven tooth number. So if you look over here, what do you see? You see that if we look at this multiplication, we'll end up with, if we derive, introduce the train ratio or value E, then we will be able, through this value, to understand what will happen to the last gear, which is number 6, knowing what is happening to the first gear, which is number 2. Okay, we'll have example about this, don't worry. So just to show you over here what happens when we have a worm. So the worm gear, ya shabab, this is like no, this is actually a crossed helical gears. I said it is worm. So this is a crossed helical gear. All right. So when you see the helical gear, you would want to worry about where the thrust is going. So, and you want to put the thrust bearing opposite to it. So in here, you see the bearing, you are changing it where according to the direction of the thrust generated on the shaft over here. And as you see, this is now telling you how the relation, when this one rotate in this direction, this one will go this direction. This is called a right-handed, and this one is called left-handed. Okay, this is just to show you the relation while the gears are rotating. Now, of course, ya shabab, if you go to the industry, with the most common multi-stage gearing is probably the most common is the gearbox in cars. And if you go to the industry, they don't usually have gearboxes there, in the sense that, oh, put it in number 1, put it in number 2, put it in number 3. You will commonly, I have to tell you, and I have seen this with myself, in most of the time, you will see when you receive in a workshop gearboxes, they are usually, most of the time, 2 stages. 2-stage compounded gears box or train is very common because there is a standard output, for example, for a turbine, and there is a standard input for a pump. And when you want that turbine to supply the power to the pump, and if the rotation is not matching, then you put a gearbox which is designed to reduce this RPM to that RPM, or increase this RPM to that RPM. So 2 stages will do. That's it. 1 stage and another. So 2-stage gearboxes are very common. Yeah, Shabab, I think I stopped here with the other class. Let me, I don't want to have a disconnect between the other 2 sections. So I will take the attendance and then we'll just speak a little bit about this, example. The next class, inshallah, we will cover it up, okay? All right. So let's see. يوسف.
موجود.
اوكي. العباد. ماجد. عياش.
موجود. العياش حسن.
عبد الرحمن.
موجود عبد الرحمن.
محمد.
موجود.
عبد العزيز. عبد العزيز are you here؟ أحمد.
موجود.
عبد الله.
موجود.
خالد.
موجود يا دكتور.
الحارثي.
يس دكتور.
سعود. سعود. حجاب. he attended with other class. سلمان.
موجود.
فارس. attended with other class. طارق.
موجود.
عمر. attended. مصطفى.
موجود يا دكتور.
علي. العمر. العمر علي. حسام.
موجود يا دكتور.
هاشم.
موجود.
سلطان.
موجود دكتور.
نايف.
موجود دكتور.
محمد.
موجود.
عبد الله.
حاضر.
مشعل.
موجود.
جعفر.
موجود.
خالد.
موجود دكتور.
مؤيد.
حاضر.
علي.
موجود دكتور.
حسن.
يس هي.
anybody else يا شباب؟
ماجد I'm here.
where يا مان؟
بس رحت وجيت.
who else؟
سعود حركان دكتور.
عبد العزيز. طيب is that all؟ anybody from that؟
ستة دكتور.
Okay شباب we have only a few minutes left, you can leave. Whoever is done can leave. That's it for today. Who؟
عبد الله الحضرمي.
Okay. All right يا شباب thank you.
دكتور.
Yes.
About the platform, I sent you an email about the Teams. You can upload it, the quiz in Microsoft Teams. But in Microsoft Teams, there is too many